This is a short series of slides to assist paraglider and hang glider pilots in using Skew T meteorological graphs. In this series, we look at 5 aspects of the Skew T graphics: where we can find them, what do they tell us, what all the lines on the graph are for, and how to read them to get some useful information. Finally, there are a few examples that may help pilots test themselves and learn. This is the section where we look at how we can read the information we need from the Skew T graph. We can begin by looking at the easy stuff on each side of the soundings graphic. Most of the sources we use display cloud on the left-hand side of the graphic. RASP also has a green line indicating rain. On the right-hand side, Skew Ts use wind barbs and lines to indicate wind speed and direction. Wind barbs have a pointed end and an end with feathers. The pointed end indicates where the wind is heading towards, while the feathered end is the direction in which the wind is coming from. The feathers themselves are an indication of the wind strength. A full-length feather is 10 knots and a half-length one is 5 knots. All feathers are added together to give an overall wind strength. Alongside the wind barbs, there is often a line indicating the changing wind strength with height. The scale of the wind strength varies according to the wind strength that the line has to cover from the surface to the top of the troposphere. We can then use the 2 temperature plots to calculate the altitude where the air will condense. When ground level air is simply washed aloft by wind and air is driven upwards by the topography of the ground, then cloud will develop at the lifting condensation level. However, if the air at ground level is warmed by the sun and then becomes sufficiently warm relative to its surroundings to rise, then that parcel of rising air will condense at the convective condensation level. To determine the condensation altitude for simple lifting of air, there is a simple 3-step process. First, we draw a line parallel to the dry adiabat, starting at the soundings temperature that was recorded at the surface. Then, we draw a second line, starting at the dew point measured at the surface, and we follow the straight trajectory of the saturation mixing ratio. The altitude where our 2 lines intersect each other is the lifting condensation level, or LCL. Of more interest to free flyers is the altitude at which air heated by the sun might condense and form cumulus cloud. This will be the top of our thermic climbs and the base of our cumulus. In this case, we very simply follow the saturation mixing ratio from the ground dew point temperature until it intersects with the environmental lapse rate line that was plotted. It is possible to reassess the true dew point of the air at your flying site using some ice, a glass of water and a thermometer. Kelly Farina of Mastering Paragliding has published a handy short video about this, which can be found using a simple web search. Search for Mastering Paragliding Dew Point Experiment. A further useful parameter can also be determined after working out the height of the convective cloud base. If a second line is drawn from the intersection of our first saturation mixing ratio line with the environmental temperature line, and this new line is drawn parallel with the standard dry adiabatic lapse rate line back down from cloud base to the Earth's surface, this will produce a temperature at the Earth's surface called the convective temperature. This is the temperature to which the Earth must be heated for thermals to rise and form cumulus. Any thermals that leave the ground before they are heated to this extent will not rise as fast or as far. As illustrated earlier when using the desktop tools in Windy, The lines we need to establish the CCL and the convective temperature appear when we float the cursor over the graph. Note that the thermals could break from the surface at any time when they become warmer than the air surrounding them. However, they won't rise as fast as those that are warmer before they break away, and these cooler thermals may not rise sufficiently high for the water vapor they contain to condense. This is true in circumstances such as those illustrated in this windy Skew T graphic, where the air above 800 hectopascals level is slightly more stable and cools less fast than the standard dry adiabatic lapse rate. It is probably worth looking in more detail at the trajectory of the environmental temperature sounding relative to the standard dry adiabatic lapse rate of a rising parcel of warm air, our thermal. In this illustration, the first 2,000 meters show a parcel of air which has been heated to around 5 degrees Celsius above the prevailing air temperature, running parallel to the environmental lapse rate line. This section of the climb is shown in purple colour. However, when the air pressure reaches 800 millibars at around 2,000 meters, the environmental air becomes more stable and is cooling at a lesser rate than the adiabatic lapse rate. This section of the thermic climb is shown in orange. This means that the forces that have been driving our parcel of air upwards, namely the fact that our thermal is warmer than the surrounding air, are now reduced. However, our thermal has got used to travelling at a steady speed upwards, and the air in the thermal has a fairly significant mass. This means that our thermal will both slow a little and get a little turbulent. Kelly Farina of Mastering Paragliding often highlights this aspect of a flying day, and it can be useful in informing pilots that our climbs may become lumpy as we approach cloud base, and we may feel that it would be faster and more comfortable to move on. A further factor to bear in mind is that we generally launch from a high place. This means that we should actually focus our attention on the sounding temperature and humidity of air at the height of our planned launch. Using this same Skew T as before, but planning a launch at 2,500 feet or around 925 millibars pressure, then the trigger temperature for any thermal has only to be a few degrees above 25 degrees Celsius rather than the valley bottom temperature, which will be a few degrees warmer. In reality, for this particular Skew T, the dew point temperature never gets anything like close enough to the soundings temperature for clouds to develop, and it seems unlikely that thermals will be hot enough to reach an altitude where condensation will occur. One great source of more explanation of the Skew T and the soundings graphic available in RASP is the video presentation given by Sean Staines of Wessex and Thames Valley hang gliding and paragliding clubs. It's available in the learning section of the Thames Valley website. Within the learning section of the main menu, you can find a specific section on Skew Ts. This image is a still extracted from Sean's really excellent presentation, and this slide shows detail of many of the points we have covered so far. In this Skew T graph, Sean points out the high cirrostratus cloud that may inhibit convection and thermal development, but he also highlights the dashed pink line that RASP uses to show the path of any available thermal. It's not terribly clear on the RASP Skew T, but where the dashed pink line changes angle, it's the point at which a line drawn parallel to the saturation mixing ratio lines would intersect with the surface dew point temperature. Accordingly, this kink in the dashed line occurs at the convective cloud base. This is a closer look at the change in direction of the dashed pink line, where the trajectory of convectively heated rising air changes from the standard dry adiabatic lapse rate to the saturated adiabatic lapse rate as the water vapor within the thermal condenses. This is another still taken from Sean's presentation, illustrating the classic egg timer shape we look upon for a really good thermic day. There is no non-convective cloud, although the temperature of the dew point and the environmental lapse rate at cloud base look sufficiently close that we can predict there will be cumulus clouds around the top of any thermals. These lines need to be within 3 or 4 degrees Celsius on the forecasted soundings for condensation to occur. A further concept for which the Skew T can be helpful is that which helps us understand the risk of thunderstorms. RASP maps this particular parameter, the convective available potential energy, or CAPE, for the day. In general, any CAPE value of 500 or more is something to pay attention to. A Skew T can help us understand where these CAPE figures come from. In this Skew T, the ledge or kink that occurs in the red environmental temperature line is quite small. The air only becomes isothermic for a couple of thousand feet, and any thermal much warmer than the environmental temperature line is not arrested after it switches from the dry adiabatic trajectory to the course described by the saturated adiabatic lapse rate trajectory. This means that the thermic parcel of air will continue to rise after the water within the parcel has condensed, and towering clouds could develop throughout the troposphere. Any situation where the trajectory of the saturated adiabat is to the right of the red environmental temperature line is a circumstance where the potential energy available for convection will be high. The actual value of the available potential energy is a function of both the height and the width of the area between these two curves, and is highlighted in this slide in red. On the RASP soundings graphic, a figure for CAPE is also generated and displayed in the text at the top of the graphic. In this case, the CAPE is over 1000, a high risk of thunderstorms. The counterpoint to circumstances where we may be concerned about CAPE and thunderstorms are circumstances where the ledge or kink described by the red temperature soundings line is large enough to arrest almost any thermal. The extent of this section of the graphic is referred to as the CIN, which stands for convective inhibition. This Skew T graphic, which comes from the service used by Steve Ham in central Spain, illustrates the way in which the red environmental temperature line is positioned to the right of the saturated adiabat, which marks the course that the convective air would take after condensation. This arrests convective cloud height and inhibits overdevelopment. In summary, one simple message to remember is that an egg timer shape with a tight waist represents a great looking day. The diverging lines above cloud base are useful features. The red line heading back to the right caps off if convective development and limits the risk of clouds getting too big. The divergence of the dew point with the blue line heading off to the left shows that the air has given up all its moisture to the cumulus, and it's a good sign that the day won't be spoiled by clouds spread out and the day shutting down early. In the final section of this series, we will present a few examples of Skew T graphics from a variety of sources. They may be of interest and help consolidate some of the information we've covered so far.